physics. But I'm planning to start working on some problems after we finish the theory. Now, I don't remember, where did we leave it last time?
We did we
The
started
Bernoulli,
on
right?
we started Bernoulli's, yeah.
Yeah. So, well, let's continue then. Remember, I will write some key things. So again, this chapter is purely on Bernoulli equations. It's a very important chapter. That's why I gave you also 2 assignments from this chapter. Especially 6, this assignment is important, and 7 too, but for civil engineers, this is more important. So conservation of mechanical principle. And I'm not gonna read all of the stuff there, but I'm gonna highlight the things that I have there, or I erased it, that it has 3 components. Well, I wrote it, one thing that I told you is to write it the way that it is in the textbook, but later on in the slides is the way that I teach my students, and we talked about that, which is this form of equation, with gamma being the unit weight of the water. And we said that this has 3 terms. This is the pressure, so this is the pressure term or pressure head. The V is the velocity, so that is the velocity head. And this is the elevation, just elevation. Not elevation head, just elevation. Okay? So now, in terms of how to apply the equation, and that's important. So we apply the equation along the streamline, okay? And let me make the analogy. In physics 211 or dynamics, let's say you have an object here, you apply a force here. I'll make it very simple now. From location 1 to location 2. And you have, either Newton's law, or you have what else, which principle you have from location 1. You have the frictional force here, obviously. You have the weight of the object and the normal force, weight and normal. You have Newton's law, and then you have the principle of work and energy, right? So I think what was the principle there? T2 minus summation of the work. I don't know if you use those symbols, but this is kinetic energy number 2 minus kinetic energy at location 1, the summation of the work of the forces from 1 to 2. The same idea, and actually Newton's law was derived from, the Bernoulli equation was derived by Newton's law as we saw it last time, but Newton's law was applied along the streamline. The same idea that we did in dynamics for an object, you're going to apply it now for a water particle. So remember, you need to apply it along a flowing fluid, okay? Now, if it is stationary, what are we missing? Which term we're going to miss? If you have a stationary fluid.
The velocity.
The velocity, right? There is no velocity, so you have the remaining 2 terms. Now, we're not going to deal, so don't worry about unsteady flow. You see there, all of a sudden, you see the integral, and you see the time. Unsteady means that it changes with time, but we're not going to deal with that. We're going to deal with steady and incompressible. Same thing with compressible flow. Compressible means that the density is not constant. That's why also the density is on the integral. So those 2 are not constant for unsteady compressible, but we're not going to deal with that case. So don't worry about that. And this is a review of what I said. We have the term P, which is the pressure head. They call it static pressure. It's okay. It's the same thing. The V square over, well, now they call it as rho V square over 2. This is not really the velocity head. The velocity head is V square over 2G, or the dynamic pressure term. And then you have the hydrostatic pressure with the component Z. Here, I just use the therm elevation Z. And then, of course, if you add those three things together, you have the total pressure. Any questions about that? Do we understand the three terms that define the Bernoulli equation? Pressure, velocity, and elevation. Now, we'll do this and then we'll do one of the examples from the assignment. So you have here a device, well, this thing shows you two devices. So this is a flow in a pipe, okay? So you see a pipe, so you have a moving fluid. And you have two types of devices that measure the